In this video, we introduce the random variable. Random variable is a mapping that maps the outcome of a random event or a random experiment to a set of real numbers. Random variables can be discrete or continuous. Let's look at a discrete random variable. Let's look at an example here. Let's considering flipping a coin. There are two outcomes. One is head, one is tail. So in this case, we want to establish a random variable x. So RV means random variable. We're going to assign it equals to 1 if the outcome of this flipping coin is tail, and 0 if the outcome is head. Therefore, in this case, a random variable x is discrete random variable. It has two values, either 1 or 0. Next, let's look at a continuous random variable. Consider wireless communication channels. And when the signal transmits through the wireless communication channels, due to the scattering and the reflection from the street, from the environment, the signal transmitted through the channel is normally attenuated. The amount of attenuation is random. It depends on the environment, and the environment can be random. So we can assign a random variable y, which I just assign equal to the amount of this attenuation. This random variable y can be any real numbers. So therefore, it is a continuous random variable. And here we focus on continuous random variables. When we talk about random variables, we talk about probability. For continuous random variables, there's a concept called probability density function. So notation is f is a function, x is the random variable, and small x is a value. So f, x, x. That's a probability density function as a PDF function. And notation-wise, random variable, we always use a big letter. Small letter x is a value. So a property of a PDF function is that if we do the integral from minus infinity to infinity of this PDF function, it always equals to 1, which means that the area underneath of the PDF function is always 1. Let's look at the PDFs for two popular random variables. One is uniform random variable, which means that the PDF function, the probability density function, has this format. So f x, small x, equals to 1 over b minus a, when x in between a and b. This is x, small x, and this is a, this is a b. And the height for this rectangular is 1 over b minus a. And then if we look at the area underneath of this PDF function, we obtain the area is 1. So that's this property. If we do the integral from minus infinity to infinity, the PDF function, then we obtain 1. The relationship between the probability and the PDF function is that if we want to obtain the probability of a random variable in between any values, a and b, this is any values, and we do the integral of the PDF function from a to b. This probability is the area underneath of this PDF function here. This is a, this is a b. That's the area of this quantity here. That's this area. Let's review the expectation and the variance. The expectation of a random variable, we multiply by x by the PDF function of random variable x, and we do the integral from minus infinity to infinity. And remember, this is a constant, it's a value, is a value. Because you do the integral from minus infinity to infinity, and it's no longer a function of small x anymore, is a value. Variance measures how far spread out this random variable from the mean. So we take a random variable, we take the random variable minus the expectation, which means that we take the difference of this random variable with the mean. And this difference can be positive, can be negative, and we make it positive. We square that. And this square is another random variable. Now we take expectation of this random variable highlighted in purple, and this is the variance. In summary, the variance of a random variable, it measures how far spread out this random variable away from the mean. So if we do a little reorganization of this expectation, and that equals to expectation of x squared. X squared, that's another random variable because x is a random variable, x squared is another random variable, and minus expectation of x and squared. And this is a constant. Expectation of x, that's constant, you take square. If we take the difference of these two terms, we obtain the variance. The property of expectation is that if a random variable is scaled by a constant, the mean is scaled. Okay. The expectation of constant, that's the same thing because there's no randomness. This constant is deterministic. So therefore, the expectation of C equals to C. What about if the random variable is shifted? It's shifted by a constant. Everything is shifted by constant C. So the expectation is shifted by C as well. Now let's look at the variance. If the random variable is scaled by C, the variance is scaled by C squared, because if we look at the definition of variance, everything involved expectation of x squared and also the expectation of bracket squared. So everything squared. What about variance of C, a constant? Is 0 because there is no randomness in this constant C. And what about if the random variable is shifted by C? The variance does not change. Remember, the variance measures how spread out this random variable away from the mean, because the mean is shifted as well. And if this is a random variable, I can assign this another random variable of y, and expectation of y equals to expectation of x plus c. And this expectation being shifted, we can do a simple justification here. Variance of y equals to expectation of y. I call it y equals to x plus c. This is another random variable. So expectation y minus expectation of y. I take squared and take expectation. Right? Expectation of y equals to x plus c. And expectation of y, using this property, the expectation means shifted. So expectation of x plus c, bracket squared. And then you can see c and c cancel out each other. That equals to expectation x minus. Right? So it is equals to variance of x. So that's this property here. Another popular random variable is Gaussian or normal random variable. Notation-wise is x, that's a random variable. And this notation means that this random variable follows normal distribution. This normal distribution, we have the mean is small m, variance is sigma squared. So the PDF function is this. This is the PDF function is e to the power minus x minus m squared divided by double of the variance, and this is the scalar to make sure the area underneath of this PDF function is 1. So for Gaussian random variables, we have expectation of Ex equals to EM and variance of Ex equals to sigma squared. And we can derive for the uniform distributed random variables, the expectation is half A plus B. That's the middle point of physically means that because this probability density is uniformly distributed from here, from A to B, so therefore the expectation of this random variable is just the middle point between A and B. The variance can be calculated using the definition that equals to B minus A squared divided by 12.